So in this video, we're not looking at a numerical problem. We're doing sort of, I suppose, a little thought experiment. So we're looking at the section on combined rotational and translational motion. So this typically arises towards the end of a motion and energy or a mechanics course, when people are sort of they've been through a lot of stuff, and maybe they start to lose focus a little bit. And I don't think it's as well understood as some other parts of the course are. So we're going to do a little thought experiment and say that we're asked to design some sort of a cart. So it's an unpowered cart, like a soapbox racer or something like that, that has to go down a hill. And obviously we want to beat the other entries. And the question we have to ask ourselves, we're at the design stage, and we have to ask ourselves, do we want big, heavy wheels or small, light ones on our soapbox racer? Does it make any difference? And how can we figure out which is better? So we can do it in terms of energy, an energy argument, and taking into account the combined center of mass motion. So if this was the center of mass motion here, it moves down the hill, and we also have the rotational motion of the wheels as they move down the hill, although they rotate in the opposite direction, but that doesn't matter. So let's just imagine this is the height, so this is the height of the hill that we have to go down. So the potential energy of the cart at the top of the hill here is mgh. So m is the mass of the cart, g is acceleration due to gravity, and h, okay, let's turn this into a small h just for convenience. And that's our potential energy at the top of the hill. So as the cart runs down the hill, that potential energy is converted into now two forms of energy. So we're not just dealing with center of mass motion anymore. We're dealing with rotational motion as well. So the wheels are rotating. So some of that energy is transferred into center of mass kinetic energy, or center of mass energy, kinetic energy, which is given by a half mv squared. So v is the velocity of the center of mass. But some of that potential energy from, by virtue of the fact that the cart is at the top of the hill, is transferred into rotational kinetic energy as well. So the formula for rotational kinetic energy is a half I omega squared. So, just in case you're in the early stages of learning this stuff, this guy here is the moment of inertia. The moment of inertia. And omega is the angular velocity. So the moment of inertia is a measure of how difficult it is to rotate something around a certain axis. And every sort of shape, every object will have its own moment of inertia, and the moment of inertia also depends on how far the mass is concentrated from the center of rotation. So you might have seen this equation here as well. I is equal to sigma m or squared. So it depends on how far the mass is distributed from the center of rotation. So we can see from that then, if m goes up, so if we look at the equation here, the moment of inertia is dependent on the mass. So if the mass of the wheels goes up, that means that the moment of inertia goes up. And if the moment of inertia goes up, that means that more of our potential energy is converted into rotational kinetic energy. And that means that there's less available to be converted into translational kinetic energy. And ultimately the center of mass, the velocity of the center of mass, is governed by how much translational kinetic energy we have, this v squared term here. So the more we take away from that, the less that our final velocity is going to be, and the slower ultimately our cart is going to be in the race. So what that tells us is, in order to win the race, in order to get our translational kinetic energy as high as possible, we want the rotational kinetic energy of the wheels to be as low as possible. And to achieve that, we need lightweight wheels with the mass distributed, closer to the center, or as close to the center as we can get them, or as we can get it. We could come up with a similar thought experiment, I suppose, as well, if you wanted to think about designing a bicycle. Okay, so let's imagine this is probably going to be a very bad drawing as usual with me. So we've got our bicycle here and our two wheels, and we'll draw it out. And okay, let's just put that there. And yeah, okay, doesn't really matter how bad my drawings are. The question we might ask ourselves is, right, so a lot of, if you watch cycling, a lot of the design is built around, or is focused on reducing the weight of the bike, or reducing the mass of the bike. And the question we might ask ourselves is there any benefit to reducing it from the body or from the frame of the bike or from the wheels? So we know from Newton's second law, F is going to be equal to m times A. So A is equal to F over m. And another way to state it, what that tells us is that if we lower or reduce the overall mass of the bicycle, that's going to give us a greater acceleration for the same force. So if we as a cyclist are capable of generating a certain force, the acceleration that force generates is going to be greater if the mass of the bike is smaller. So that's not too big of a surprise. The question we could ask then is there any benefit to reducing the weight of the wheels over the weight of the frame? And the answer is, if we reduce the weight of the wheels, we reduce their moment of inertia. So we said I is equal to sigma m or squared. So we reduced the weight of the wheels. We reduced their moment of inertia because we reduced their mass. Sorry, I'm using mass and weight interchangeably here, and I probably shouldn't be. But we reduced the wheels, we reduced the moment of inertia, and what that will tell us then is that the torque that we need is lower then. So the torque that we need to apply to the wheel to get a certain angular acceleration. So another equation from angular motion we'll see is that tau is equal to I times alpha. So this here is the torque. This here, we'll just abbreviate it as the MOI, or moment of inertia. And alpha now is the angular acceleration. So we've said that we're going to reduce the mass of the wheels. Reducing the mass of the wheels is going to reduce the moment of inertia. Reducing the moment of inertia, which is this term here, is going to mean that we need a lower torque for the same angular acceleration. So basically, in plain English, it's going to be easier for us to rotate those wheels with the force generated by our legs if the moment of inertia and thus the mass is lower. So in reducing the mass of the wheels, we get a double benefit. We reduce the overall mass of the bike, which means that we get a bigger acceleration for our force, and we also make it easier to rotate the wheels, so we have to apply a lower torque to get the same angular acceleration of the wheels.